Hi, everyone, and welcome to our HVAC and heat pump session. We've got a full house today joining us. And actually, personally, I'm looking forward to this session quite a bit. Maybe that's from Africa and we need a lot of air conditioning there. But at the same time, it's something I've been writing and covering for almost a decade now. Actually, it's 10 years next year. And I've spent a fair share of my time climbing around cat ladders onto rooftops or crawling in basements to see equipment. And my friends still tease me when I look at the ducting whenever we walk through a mall. But, on a more serious note, it's about time the conversation moves to natural refrigerants and air conditioning in Europe, not just around refrigeration. This is really where we can make a big difference to save the planet. We keep warming the world by trying to make it cool. And I'm glad that we today are joined by some experts who are using natural solutions to show us that it's not only possible, but profitable. So that's why, we've got quite a lineup today, and I'll introduce each speaker briefly before sharing their presentation. Be sure to check the live discussion box to also submit your questions throughout. And there's also a bit of a poll if you want to take part. But then, I think we'll have a bit of a chat after each session, and then maybe after the first three, take some questions, and after the rest. But we'll see how it goes and how our time allows. But either way, let's get the show on the road. It's my pleasure to introduce our first presenter, G Christensen. I'm not going to butcher your middle name, but welcome, Managing Director of Fenagy. You're going to be talking to us about industrial heat pumps with CO2 as refrigerant. You've been educated in DTU back in '95 and further educated in engineering, business administration. You've done a lot of degrees that's relevant to this industry. But now you're working with Fenagy is a startup, to create a professional OEM in the field of industrial refrigerant and electrical heat pumps based on CO2 as refrigerant. So over to you. Exciting to see what you guys are up to. Thank you very much.
Thank you very much. I will just start sharing my screen. It should be possible here. I guess that works.
All good.
So, yes, thank you for the introduction. And of course, I've been looking forward to this moment. I would have liked to meet you all live in person, but we have to do it this way. These case stories and presentations are very short, so I made a little bit longer presentation. Some of the slides I would jump over. And of course, everybody is welcome to contact me afterwards on the slides that I didn't spend much time on. So my presentation is divided into 4 sections. First, a little bit about the challenge that we look into, a little bit about the company that we are operating here in Denmark, a little bit about the technology, and then the actual air-to-water heat pump that I would like to talk about. So to start with, their challenge, and it's a good one, actually. We do call it here in Denmark, we call it smoke-free heating. And this is because that we want to go fossil fuel-free, of course, but we have implemented a lot of biomass lately, and we burn it. And this is also what we want to get away from. And the final solution is actually to electrify our heating system. And this is what we do with electrical heat pumps. And this is why it becomes extremely popular. So the Fenagy challenge is to support the market with electrical heat pumps, but we also have another I would say segment that we look into, and that is, I think, more ordinary industrial refrigeration systems. So we do both, basically. So, I mean, industrial refrigeration systems will eventually also be heat pumps. That is at least our philosophy, because we believe that we will not see any refrigeration system just rejecting heat to ambient. We would try to use all that heat in an efficient way into our heating system. And this is why we do work with a lot of systems where we are both supporting with refrigeration on the cold side, but on the warm side, we are supporting, for instance, a district heating system with heat. So this is the challenge that we are looking at, and Fenagy is a newly started company. We are 25 people working here, and we do heat pumps and refrigeration systems, but we only focus on CO2 as refrigerant. That is our focus area. And that's about it I want to say about Fenagy. I would like to present the two figures to the right. And you probably see the map of Denmark, and you see a lot of dots there. This is all the dots where there's already placed heat pumps in Denmark, and they are approximately 350 megawatt heat coming from heat pumps, supplying heat into the district heating systems of variable sizes. Most of the bigger heat pumps are with ammonia, and the smaller heat pumps are with various different refrigerants. And only lately, CO2 has become one of these alternatives. And the figure below, to the right, here is actually the installed capacity, but based on electrical capacity, not heating capacity, but electrical capacity. And you see today we are proud around this 150 megawatt, which corresponds to the 350 megawatt heat. And you see a pretty steep curve. And this is actually the predictions from the Danish Energy Agency, which is a very nice curve if you are into this segment. But you would find similar growth curves if you look at the countries around Denmark in the northern part of Europe. So it's really, really interesting. And we do expect that in 8 years from now, in 2030, there will be 2,000 megawatt installed just that year. So we believe that the heat pump segment will be just as big as the industrial refrigeration segment in a few years from now. So what do? We make a pretty simple heat pump, and the layout is shown here. You see a outdoor evaporator, because what we're primarily doing, we are taking heat from surrounding air. The refrigerant evaporates here, and we take the gas to the empty compressor and compress it, and we reject the heat into the district heating system here. The gas is coming back from the high pressure side back to the receiver, and the liquid line goes to the evaporator again. And what you can see is that we're using a high pressure ejector and we're using parallel compression. So this is the basics of the system. Of course, an air to water heat pump have to be able to defrost. During days where the ambient temperature is below approximately 5 degrees C, ice will form on the evaporator and we have to defrost. And the way we do that is with a glycol loop, where we are basically cooling down the return water temperature to the heat pump by the glycol, and the glycol is heated, and we have a separate circuit inside the evaporator to be able to defrost the evaporator. So Danish district heating conditions would typically be 75, maybe 70 degrees on the supply temperature and around 40 degrees on return water. And this is also the case in this small case story I would show you a little bit later. The challenges for Fenagy to develop this heat pump has not, been to find components, because they are already there. But to enhance the CUP is the challenging part. So what we have developed is our own ejector system, and we also developed our own controls. So we have our own control algorithm for the entire heat pump, and we're using a Siemens hardware platform too, as PLC. So that is the basic design. The trick with CO2 is that we have, of course, in a heat pump, we have to heat water, and there's a glide from, for example, the 40 degrees C to the 70 degrees C. And you see that glide matches pretty well the glide you have on the CO2 side, where we're cooling down the gas. And that match is brilliant, actually, in district heating, because if you compare to a condensing refrigerant, it could be ammonia, for instance, you have this condensation plateau where you have a pinch point in the heat exchanger line here. So you have to push the condensation pressure pretty high to get the 70 degrees. So CO2 is really good for heat pumps in district heating systems here in Denmark. The ejector is something that we did choose because of efficiency, of course. And just to give you an impression of what does it give us, what does it bring to the table. A normal cycle without parallel compression is, let's say, minus 7% compared to the baseline. A baseline is a system with parallel compression, and having a high pressure ejector with a lift of 14 bar can give us additional, let's say, around 6%. And the good thing with the ejector in a heat pump is that we are always operating at high pressure. So all the operational hours would be perfect with the ejector. It's not like a refrigeration system where part of the season we are running very low on condensation side, and therefore the ejector performance of the ejector would be very low. Here it's full operation all the time. Next step, of course, would be looking at expander technology, because that could bring even more benefit to the system, but it's a little bit more difficult to do. We're working on it, but that will be in the future. I will skip this slide due to time. It's a little bit more around the benefits of the ejector, and show you this slide instead. This is actually the heat pump that we installed in a small district heating system here close to Aarhus. It's a heat pump of 600 kilowatt. And the idea is that we can configure this heat pump for air to water, water to water, and we can even configure that as a chiller, either air cooled or water cooled. In this case, it's of course an air to water heat pump. Therefore, we have an outdoor evaporator, and we have a gas cooler rejecting the heat to the district heating system. Of course, this is just a small slide of the various systems that we do produce of different sizes. The biggest one we produce is up to 2 megawatt to the right, and a small one, a fully integrated solution, around 300 kilowatts. So we're not doing small heat pumps, but we are not doing very, very big heat pumps either. At the district heating system, at the small district heating company here in Aarhus, the integration of the heat pump looks like this. You basically have a huge water storage. This is very important for the heat pump, because that makes the heat pump able to produce the heat when it's not used. And that is the flexible system in the electrical system, that we are using the electricity when it's cheap. We store the heat in the huge hot water tank, and we use it when it's cold outside during night or whenever. So we have a completely decouple of production and use. This district heating system are mainly fired by biomass straw in straw boilers, and they have an oil backup. So you see here is the evaporators, the outdoor evaporators, taking the heat out of the air, and the piping, and you see this small cabinet here, and inside the cabinet we have the heat pump, and it's connected to the district heating system. So pretty simple system for 600 kilowatt. Low sound level because we have the neighbor boundary here, so we have to keep around 50 dBA there, and the footprint of the evaporators is around 40 square meters. What is important with an air-to-water heat pump is the air side. What we would like to avoid is a cold air shortcut, which means that we do not want to suck the cold air back into the evaporator. So we want to use fresh air all the time, and therefore we did simulations to look at different wind velocities. And you definitely see when it's more windy, above 5 meters per second, the cold air just disappears. But if you are at very silent days with very low wind speed, there could be some recirculation. It was not something that we could measure in the project, but it's something that we have to be aware of, that we're not recirculating cold air to the evaporator, because that would really damage the COP. The other thing is, of course, defrost. And defrost is important because we are running evaporation temperatures lower than 0, and the humid air with condensate and form ice on the coil. There's a lot of tricks here that has to be done, but main principle is that it is really easy with the cold or the hot glycol defrost system to defrost the actual coil. But what we should be aware of is that we are not bringing, there could be ice forming on the fans, there could be ice on the fan protection and the casing. And this has to be avoided. Otherwise, you know, for a long period of time, let's say 1 month of low temperature, it would be an ice ball. So we have to be very careful about that. We are running with 5 to 6 millimeter distance in the fins. We are using what we call seawater aluminium, ALMG, which works fine regarding corrosion. And then we have this defrost sequence that you can study here. So that is more or less the defrost system. You also have in the upper right corner a little picture of how we actually get an idea of the defrost system. Another thing which is important, of course, is what did we expect from the COP and what did we actually measure? And the blue curve here is what we expected, the simulated COP, the simulated heating capacities, and here the yellow curve is the simulated COP values. And you see that we have very little difference on the capacity. Capacity was within a few percent, let's say 2%. However, the COP was quite a bit lower, up to 5 to 6% lower than what we expected. And this is due to pressure drop in the system that we did not simulate correctly, and its compressor efficiency, which is a little bit still inside the EN 12900, but on a little bit on the negative side. And this is what we have to be very careful about promising data on heat pumps. It's not like refrigeration systems where we, you know, if the temperature is cold enough, people are happy. In this case, with heat pumps, we have to deliver a temperature, we have to deliver a capacity, and we have to deliver the COP we promised. Otherwise, there are certain penalty schemes, and we have to pay back to the utility company. And that's how it works. Conclusions. Well, we believe that definitely CO2 would be the right refrigerant for these air-to-water heat pumps. We have a lot of orders, actually. We're working on 6 bigger installations just here in Denmark right now. So definitely CO2 have a good chance in the mid-range, mid-capacity range of heat pumps. We do see low noise, low vibrations. There's really advantages here because these district heating systems are close to cities. Very little footprint. We have redundancy because we have more than one compressor. We have many compressors on these units. And we lose very little capacity during defrost, and we are able to supply stable temperatures. Then we also see that that we are in a good range in all temperatures, ambient temperatures. We can operate from -20 to +20, which we have to be able to offer. And COP, we still have to work on COP. You are never good enough, so we will definitely try to improve the future systems as well. So that was more or less my quick presentation. I'm not sure about my timing here.
You're okay. Thank you so much, Ken. You can stop sharing on that one.
Yeah.
It's interesting to see that there's, I mean, I think CO2 heat pumps are such an important conversation to have, and especially as Europe and other countries really look at decarbonization of the sector. Have you been, as the business been growing, has there been increased demand for this? As any of the, are you seeing what is driving this?
But clearly, it's a transition. It's a green transition. Heating systems all over Europe is part of the conversion away from fossil fuels to the electrification of the entire society, and this is what we are looking at here. So we are of course in competition with small domestic heat pumps. We see a lot of local houses, private houses having heat pumps. And of course, what we benefit from here is that district heating is very well established in Denmark. We have like 70% of the district heating system, of the heating used in Denmark is connected to district heating. So we are tapping into that movement of electrification of the heating system. So we see good growth here, definitely.
Denmark always leads by a good example. Thank you. Yeah, you can stop sharing your screen and then I can introduce. It's always tricky to find that button again with so many screens floating around. Maybe it should be on your Zoom. There you go.
Yeah. Sorry.
No, thank you so much. Luca, are you guys ready for the next? You'll be your next up. Let me introduce our next speakers. I hope they're ready. It's always hard to tell when everyone's, they are. So let me introduce you. Okay, so next up we've got so many speakers here. We've got Luca Rossi, project manager at Biaggini, and he's joined by Andrea Skory, technical manager at Migros. And they're going to be talking about a Swiss shopping mall, which implemented a 600 kilowatt CO2 reversible heat pump chiller. So I mean, you're both very experienced. I think we're going to waste the whole session if I go into too much detail about everyone's bios, but it is also on the speakers. If anyone using the platform can just check there. But yeah, I would rather let you talk than me talk. So take it away.
Thank you.
The hardest part is always getting technology to do what you want it to do. Let's see, we'll get the
Okay, so
we can see both the screens now. Sorry, look, that shows the next one as well. Yeah. I think we were having this issue as well yesterday. I think if you go to the settings at the top, there should be one, and one of the drop-down menus of those 3 buttons above your presentation. I think it's always a bit tricky when you're sharing multiple screens.
Luca, sorry, if you go to the top menu, in impostazioni di visualizzazioni, then you have to click there and change the setting.
This one?
Yes.
Okay, so
thanks, Luan. Perfect. Yeah, we're good to go.
So good afternoon, everyone. I'm Luca Rossi from Biaggini Frigoriferi, project manager in the technical office, and close to me there is Mr. Andrea Skory, technical manager in Migros Ticino, one of the most important retail chain in Switzerland. Today we want to introduce and show you the latest project installed in the Italian region of Switzerland. Therefore, 2 reversible heat pump chillers with a capacity up to 600 kilowatt, able to cool and to heat the whole shopping mall. The installation is located in Agno, a small town close to better known Lugano in Switzerland, very close to the airport. And Mr. Andrea Skory is the father of this project because he had the idea of this installation just after ATMO 2018, when he asked me to size a system able to cool and to heat the whole shopping mall, replacing the old systems. The project started in 2020 with the design of the units and the main additional devices. And the installation on site was done during last spring, and the commissioning has been completed in June 2021. The goals of the project were, first of all, to replace the old technology installed in the shopping mall, so that the two old burners for heating, they had a capacity around 650 kilowatt, to replace the old HFC cooling machine with a capacity around 434 kilowatt, fed with air 407C, with external water cooling towers, and to install an unique system able to satisfy all the energy requirements of the shopping mall, so that heating and cooling. Obviously, to decrease the GWP of the installation, one of the most important goal of Migros in the whole Switzerland, and also to guarantee better thermohygrometric conditions in warm and cold season, better than in the past years. Obviously, to improve the efficiency and to decrease the energy consumption of the installation. And the last objective was to make Migros Agno the first shopping mall in our region fed with this kind of installation with natural gas CO2. Among several proposals, the customer chose our solution, so that two reversible heat pump chillers with indoor units and outdoor gas cooler evaporators. Each unit is fed with 3 pieces compressor door-in CD 3401H on the URE unit, with a double frequency variator for each machine, with a low pressure design of 80 bar and a high pressure design of 120 bar. We can see the simplified operational drawing when we see the compressor, the main devices, so that the 3 compressors, the gas cooler, alpha lava gas cooler to heat water, the chiller evaporator to cool the water, and the external devices. The 2 units are managed totally by Honeywell by Schneider electric controllers. In this picture, we can see the 2 units, very compact units with a length around 3 meters, no more. We can see the most important devices, so that the evaporator, the gas cooler, the 3 compressors, the electrical box on board, and the horizontal liquid receiver. As already mentioned, the units are able to run in reversible mode, so that now in summer and in quite warm months, the units are running in chiller mode. We can see in this picture on the simplified operation scheme, in the red line, the cycle operating just now, so that the 3 compressors are running with a discharge pressure around 94 bar, with an external temperature around 35 degrees. 3-way valve, the external device running as a gas cooler, a sub-cooler, the high pressure valve, the liquid receiver, and the chiller evaporator fed with an expansion valve, able to cool down the water from 14 degrees to 8 degrees. In the heat pump mode, we can assume that all the 3 compressors in most cold season will run with a discharge pressure around 84 bar. In this situation, the 3-way valve will send the CO2 mass flow into the gas cooler plate exchanger, able to heat the water from 27 degrees up to 37 degrees. The three-way valve system switches the external evaporator from gas cooler to evaporator device, so that with this external device, we absorb heat from the external air. We have a liquid receiver, which in heat pump mode is at the same pressure of the suction pressure of the compressors, and the subcooler, the same subcooler exchanger, which in summer works as a subcooler to improve the COP of the unit, in the winter has the goal to heat the suction line of the CO2 to guarantee a minimum superheating of the compressors. In the defrosting cycle, the last cycle of this unit, we will make the first compressor run at minimum frequency, and the external device will work as a gas cooler, because the external device has a double coils, gas cooler and evaporator, because we send the hot gas always in the gas cooler coil and never into the evaporator coil to avoid thermal stresses into the coils, and fan rotation will be reversed to optimize the defrosting cycle and dropping of water droplets, so that we can say that the defrosting cycle is quite a hybrid configuration between reversed cycle and hot gas defrosting cycle. We can see in the next slide 3 pictures of the units installed into the technical room of the shopping mall, and we can highlight the main features of the unit. In chiller mode, each unit has a capacity of 250 kilowatt with an external temperature around 35 degrees. The water will be cooled from 14 to 8 degrees. The low pressure design is 80 bar. The high pressure design is 120 bar. Each unit has a double frequency variator, which manage the frequency variator on the 2 compressors among 25 and 70 Hertz, and the external device works as a gas cooler. Otherwise, in heat pump mode, the capacity of each unit is around 300 kilowatt with an external temperature around -7 degrees. The water will be heated from 27 up to 37 degrees. The low pressure design of the 2 stages is the same as chiller mode, so that 80 bar for the low pressure stage and 120 bar for the high pressure stage, double frequency variator, and the external device works in this situation as evaporator. Both the 2 units and both the wall system, so that the water tanks, the warm water tanks and cold water tanks, are totally managed by controllers delivered and installed on the electrical box by Honeywell, by Schneider Electric. We can see a simplified operation scheme. Each unit is fed with a WCM 9000 Pro, able to manage the single unit, and there is installed in the first electrical box on the 2 units in AVD device able to coordinate the 2 units and to manage the wall heating or cooling system. At the end, the external device is a totally customized LUVE device with double coil, evaporator and gas cooler coils, because as already highlighted to you, we prefer to separate the two operational goals of the device to guarantee the best performances in both in heat pump and chiller mode, and also to avoid stresses during the defrosting cycle. You can see in these pictures the double LUVE devices, totally independent. So each unit installed in the technical room has its own external double gas cooler evaporator. In conclusion, we can resume the first feedbacks and savings with this new R744 system. The performances are better than the old system. In the shopping mall, there are more comfortable and accurate conditions, and in the supermarket inside the shopping mall as well. For example, there is no more water condensation on the closed cabinet doors, thanks to the lower humidity in the air and to the lower temperature of cooled water, differently from past years. The energy consumption measured during these first running months are among 10 and 15% lower than past years, despite the old machines worked with evaporative cooling tower outdoor. The heating recovery is able to make post-heating in the ventilation system. The redundancy of the units guarantees to follow the energy demand curve of the building very accurately, thanks to, for example, to the double frequency variators installed on each unit. No failure or breakdown until now, thanks also to remote surveillance and management 24 hours every day. The units are able to remain stopped without danger, thanks to the high pressure design. I remind that the low pressure design is 80 bar. There is a unique and reliable plant for heating and cooling. It means that the customer will have lower maintenance costs. And Migros Agno is now 100% HFC free, and the building doesn't produce greenhouse or pollutant gases. And I want to thank to the main company involved in this project, LUVE, Eliwell, Dorin, Alfa Laval, Urre, for the delivery of the unit, Sporna. And thank you for listening.
Thanks, Luca. I wanted to have a question for Andrea, maybe. Was it a difficult choice to make to go to CO2? I mean, it obviously paid off in the end, but was it a difficult decision to make or to motivate for the company?
È stato difficile scegliere CO2 come soluzione per questo tipo di installazione?
No, la scelta è chiara, per noi la direzione è stata quella di certa soluzioni.
Yes, and Andrea says me that the choice was easy and clear, because CO2 is now the only way, the only choice for the Migros retail chain in Ticino, in our region, and in the whole Switzerland as well.
That is amazing to hear. The rest of the world can definitely take from your example. Thank you both so much. I appreciate it. Let's see who's next on our list. I think it's your turn, Kenneth. Are you ready? Our next speaker is Kenneth Hoffmann, the product manager from GA, who's going to tell us about, the GA, GEA. Every country I go to, they pronounce it differently. But the 6 megawatt ammonia heat pump and how it's turning energy from a coal mine into renewable heating. Yeah, it's a great topic to see ammonia and what you guys are doing as well.
Yeah, thank you very much, Ilana.
We can't see your screen. It's just black.
Can't. Oh, that's not good.
Yeah.
I'll try and share again then.
Okay, let's see. Not to stop your momentum there.
That's all right. So, okay. So we try again. Just a second.
No problem. That's one of those things you can overplan all you want, but on the day the technology never does what you want it to do. We've all been there.
Shit. I also do this. So, do you?
Let's see. Yes, there you go. You're good to go. Thanks, Kenneth.
All right, good. So, I'm happy to be here to tell a bit about the projects we have been doing. There is, as Kim also said, there's a lot of investment into heat pumps, into district heating going on across Europe. I'll tell a bit about a project we have done in the UK. Let's see. So it's a 6 megawatt of ammonia heat pump we have installed in Gateshead, which is just south of Newcastle. Gateshead, they have a long history of coal mining. Already back in 1344, they started digging coal. And in 1625, they were the world's biggest coal supplier, digging out 400,000 tons. You need to be aware that this is before the Industrial Revolution. So all these coals have basically been used for heating up homes. And that's actually what makes this interesting. So although the coal mine is now used, and since then they've been filled up with water that have sieved into these coal mines, we can now use the energy from these coal mines again. Instead of having dirt and dust and CO2 emissions, we are now creating clean energy from that energy we are able to take out of the coal mines. Regarding coal mines in UK, there is quite a lot of coal mines across, and all these coal mines they have been very well mapped out by the coal authorities, so they know exactly where the tunnels are, and also what the flow rates are within them. So when you start drilling down and taking water out of these coal mines, that they know with very high certainty of if you take the water from here and put it back down here, you don't get short circuiting of the water stream, so you end up taking up the cold water again. And that's one of the big challenges with ground source heat pumps, is that the drilling is often a bit of a lottery, that no matter how much investigation you have done beforehand, when you start drilling, you don't know how much water you are actually getting up, and you have a good idea of the temperatures of it, but the amount of water often varies a lot, and that's what we have seen on several other projects. I think this is our fourth or fifth ground source heat pump in the UK, so this is the first one where we take the water directly from coal mines. So, and a lot of these coal mines, they are actually already today pumping out the water, because if the water level in the coal mine raises too high, it can start contaminating the fresh water that people are drinking. So there's actually already being pumped out water. So instead of this just being pumped out and put into the rivers, it's actually better to take the heat out before you get rid of this water. So the project in Gateshead, they started in 2015. This is not like Denmark, where 70% have district heating already. In UK, this is a segment that is starting to be built up. And in 2015, they started in Gateshead with their first district heating scheme. And that was then based on CHP, so gas engines, where they started building out to some council housing and some council buildings. But they hope to expand it, and not only getting the council buildings included in this, but also private homes and both industry and non-industrial businesses involved in this. So by 2030, they hope that 17% of the heat of the homes in the area will be connected to the district heating network, and 24% of the non-industrial businesses and public sector should also be connected. So by then, they hope to have 12 gigawatt hours of heat into the network. So that's, of course, a lot more than they can provide with the two CHP engines they installed in 2015. And that's where we came in with the second phase of this build up of renewable heating for the homes in Gateshead. So we have installed 2 heat pumps. It's 4 compressors, 2 low stage, 2 high stage compressors, because we need, the water is coming out of the ground at 15 degrees. It's cooled around 6 degrees before we put it back down into the coal mines. And so we take out around 4 megawatt of heat from there. The 2-stage heat pump are then first raising the temperatures from these 6 degrees and then up to an intermediate pressure of around 35 degrees, and then again raised up to 80 degrees, because the district heating network is laid out for 80 degrees, and the return water is 65 degrees in this heating network. It's not like Kim was talking about, the heating network where you have 40 degrees return. The heating in the homes are simply not designed for this. They have been used to having gas boilers and 80 degrees in the radiators, and not all of them are very well insulated. So there needs to be quite a high temperature for the hot water supply, and the return water is difficult to get down. We have worked on several projects in the UK, and although they have plans and ideas of reducing the return hot water temperature, you rarely see district heating networks in the UK where the return water is less than 50 degrees. But there is, of course, hope that in the future the return water will become lower. So this heat pump is giving a COP of 2.9, and that is lucky, because that is exactly what the government wanted from this type of heat pump, for it to partly fund the project. There has been an RHI scheme in the UK which ends in March next year, but to be able to get funding from that, you need to have a heat pump COP of minimum 2.9, and because it runs out in March next year, we have seen over the last couple of months, I think it's in total 6 large heat pumps that we have need to be installed before March next year. So by that time, hopefully there will be 12 megawatt of ammonia heat pumps delivering district heating under the RHI scheme. Of course, the next scheme runs out March next year, it's a bit unclear what else comes in place, but the government in UK are clear that there is needed further investment into the district heating, and new schemes are planned to fund these installation. So the installation is basically 2 heat pumps, 2 times 3 megawatt. So the first one placed in series. So the first one is heating the water up from 65 to 72.5, and then the second one 72.5 to 80 to improve the efficiency further of this installation. So here is a picture of the installation, how it should be. It's not yet finalized, so there's not an actual picture of the installation. But what we see is that the choice was easy to go with ammonia, as the requirement in from the government that you need to have a minimum COP of 2.9. There was not any other refrigerant available that were able to achieve this within the design criteria that was given for this one. And of course, there is a lot of concern regarding using of F-gas refrigerant. What will happen in the future, especially with now UK have become gone out of EU, but that doesn't mean that the F-gas legislation will also be renewed or reviewed in UK. So there is as much uncertainty of what will happen in the future for F-gases in the UK as there is in the rest of EU. So that is in brief what I had on this project here. Thank you.
Thanks so much, Kenneth. That's actually a really good point that you make about the UK. From our conversations with them, they've actually said they want to be more ambitious with their F-gas legislation than in the EU. Yeah. So I think it's good for clients to actually future-proof their installations like this. How long what is the life expectancy of the system? How long? I mean, I know ammonia systems, some of them last forever, so to speak.
Yeah, as I said, the moving part, the compressor, can take it apart and refurbish it so it's as good as again. So basically you can keep running it, but we say that 20-25 years life on these kind of systems. That's minimum expected. And of course, if you take good care of it and maintenance, it can run longer time than that. So
great. I think if you can stop sharing, then we can maybe have a look. I think. Thank you. I mean, in the meantime, before we move on to the next speaker, I don't know if the audience have noticed, and now in your chat box where the questions are, there's also a poll if you go to the 3rd tab, and the question is specifically about industrial air conditioning applications, because I feel a lot of the presentations today are about that. And it's like, how long do you think Europe needs before it can switch over completely to natural refrigerants in these applications, and industrial refrigerants specifically? Industrial refrigeration, and it ranges the answers from switching over today to it won't ever be possible. And currently, at least 20% of people think we can switch over today, but 60% currently, majority thinks we need 6 to 10 years. So yeah, if you haven't voted yet, let's have a vote. How long do you think we need, Kenneth?
It's sure. I think that we can do a lot today, but I think it's also a matter of us building the resources behind. When Kim said that it needs to be installed 2,000 megawatt in 2030 or whenever it was, I think we need a lot of resources to be able to do that sort of installation. So that's where it is. I think we are ready to deliver the heat pumps, but not in that big amount. I think we need to build up resources for that.
Well, let's see. I'm sure it's still coming in future.
Yes.
Great. So the next up, we're going to move over to McDermott from J&E Hall, who's the Process, Marine and Applied Refrigeration Director. He's going to be talking to us, carry on the conversation about ammonia, but looking at ammonia-based heat pump system for district heating application in Switzerland. Switzerland is really leading the charge here. So yeah, over to you, Graham.
Okay, thank you very much. Yeah, so I'm going to talk to you a little bit about why we need, I think, to start encouraging the use of heat pumps a little bit more, and why we need to focus on the use of natural refrigerants. And then I'll talk a little bit about some of the projects that we've carried out recently with our ammonia heat pumps over in Switzerland. So just a little bit about J&E Hall. We're part of the Daikin group. And we are based in the UK, but we actually carry out contracting worldwide. J&E Hall has actually been in refrigeration for a very long time. We started in the late 1800s, and it's quite, I find it quite amusing that we started off in the 1800s using CO2 and ammonia. And then we moved away to non-natural refrigerants, to HFCs and other things. And now we've gone full circle and people are realizing more and more that natural refrigerants are the future, and we're learning from the past. Some of the speakers have already touched on this, the fact that with legislation, certainly within Europe, but also around the world, the phasing out of HFC refrigerants is forcing people and making people look at natural refrigerants more and more. And at J&E Hall and other companies, we've got a long history of working with ammonia, hydrocarbons and CO2. And it's definitely something that we need to encourage customers and end users to think about, is using natural refrigerants and moving away from the HFCs that they're used to. So now I'd just like to talk a little bit about why I think it's important that we use heat pumps. So in a traditional refrigeration, industrial refrigeration installation in the past, we would have a chiller where we have a heat source to be cooled. We cool down the heat source in the evaporator. We compress it in the compressor, and then all of that energy and that heat is just rejected to atmosphere and wasted. And it just disappears. And in the past, people weren't particularly worried about that, but people are starting to understand now that we can't just waste the heat and the energy that we've got. So by converting it to a heat pump, you can still cool down your process, whatever it is. You still have a similar system with your evaporator and your compressor, but now instead of throwing the heat away, we can recover that heat and we can use it somewhere. And I think the main difference between a heat pump and a traditional chiller with heat recovery is the temperatures. That for the heat to be useful, certainly in things like district heating, we need to have water temperatures of 70, 75, 80 degrees C. So it's, I think, a very important development that we start looking at the heat pumps. The main reason why we want to look at a heat pump is if you've got a cooling duty and heating, you can have, the way we measure efficiency is to look at the COP, which people have already spoken about today. If you have a separate chiller and gas boiler producing 800 kilowatts worth of cooling and 1000 kilowatts worth of heating, you've actually got to put a lot of energy in there to get that amount of heating and cooling out. And the COP, depending on the conditions, could be around 1.25 for the combined system. If you use a heat pump where you're taking the waste heat from the chiller and generating useful heat for your heating system, the amount of energy goes down from 1500 kilowatts to 300 kilowatts, and the COP goes up to 6. So the savings that people can make this a no-brainer. It's a very easy choice for people to look at using heat pumps. Obviously, if you have a heat pump, you need two things. You need a source of the heat, So that could be a process cooling system, cooling down power generation or heat from the air conditioning that you've got, or taking water from river or sea or groundwater or heat from the air. But you then need to match that with a heat sink, somewhere where you can put that heat. And that could be something like district heating. It could be if you have a process that requires large amounts of heat, preheating boiler water, or putting water directly into the central heating or the hot water system. And I think we need to, as an industry and as end users, think about how we can better match our cooling needs and our heating needs and marry them together and combine them into a single solution. So I'd just like to go through a couple of the projects that we've done recently. So one of them was for a power generation and district heating system over in Switzerland. The customer originally had oil-powered boilers, but they wanted to increase the amount of renewable energy that they're using. So they were going to a new wood chip boiler system and installing a new water source heat pump. So J&E Hall were asked to prepare a design, and we came up with a design with an ammonia heat pump that could deliver cooling from about 700 kilowatts to 2.5 megawatts. The heat source was cooling water from their electricity generators. So we were cooling water down to 20 degrees C, and we were providing hot water at 70 degrees C into their district heating system. Some of the challenges that we faced was that both the cooling water and the hot water, the temperatures and flow rates could vary very suddenly. And because we were replacing existing equipment, we had to design the new heat pump to fit into a width no more than 1.8 meters wide. And again, I think as Kenneth mentioned in his presentation to begin with, the aim of a heat pump is to deliver heat at the temperature that you say, at the quantity you say, but also as efficiently as possible. So what we did is we actually put a system together where the hot water comes in and it goes through a normal condenser, plate condenser, but we then put it through a desuperheater and then through an oil cooler, so we could squeeze every drop of heat that we could and every drop of temperature we could out of the system. So the customer had a target for us to have a COP of 4.4. And with that system, we actually, when it was installed and commissioned, the COP for heating was about 5, which was about 15% improvement on what we said it could do. And the heat pump was also very able to cope with the changing operating conditions and is very stable in operation. We then had a very similar application where it was a district heating network, and they wanted to increase the amount of renewable energy used to their district heating. In this case, they had a water treatment plant that was generating heat that needed to be cooled down. So again, it was a heating capacity of about 8 megawatts up to 1600 kilowatts. The cooling water temperatures varied throughout the year. So we have an inlet temperature of anything between 19 and 2 degrees C. And water out to the district heating system was required at 75 degrees C. And again, it was a similar challenges that the flow rates and the temperatures on both sides could vary quite dramatically. And that we also had to fit it into an existing plant room, so space was limited. So again, you can see a drawing of the heat pump, and it's got a traditional heat pump components. It's got the compressor and the motors, a plate heat exchanger for cooling down the water. And then again, we have this circuit design of a water-cooled condenser feeding into a desuperheater and then into a plate, shell and plate oil cooler to get as much heat out of the system as possible. And again, you can see the circuit diagram, the simple circuit diagram there showing the water circuit going through the heat exchangers in series. So in conclusion, I think my points are that today, in today's climate, throwing away waste heat isn't acceptable anymore. As responsible end users, designers, installers and manufacturers, we should be looking at how we can use heat pumps going forward. I think we need to be more innovative in the way that we match our heating and cooling demands. And we can't treat the two systems as separate anymore. They've got to be a common solution, and we need to find ways of matching that. And I think my message to end users is don't be scared of natural refrigerants. I often speak to customers and they're concerned about the flammability or the high pressures of ammonia, hydrocarbons and CO2, but they've been around a long time. The industry knows how to make use of these refrigerants and they've got a long future, and we can manage the risks or the perceived risks of them going forward. Thank you.
Thanks, Graham. I think that's such an important way of putting it, like perceived risks. I think there's a lot of fear mongering out in the world and people are very scared of using ammonia, but like you say, ammonia is probably the oldest refrigerant, and there's people that have worked with it safely for so long. And if you leave it to the experts, there won't really be a challenge. And I think also the point of like having integrated systems and not looking at your heating and cooling separately. I think that's where a lot of energy is wasted. For this particular, I mean, it's also good to see all the different applications and different success stories. Like, for which applications can you use this product, specifically the ammonia heat pump? Like, is there a certain range where it wouldn't work, or where is it suitable for?
I think we've seen quite a lot of applications today for ammonia and for CO2 heat pumps. I don't think there's any application that it's not suitable for. In the UK, there's been a lot of work on decarbonising the heating systems. There are some limitations if you're replacing existing boilers. Putting an ammonia heat pump in can be difficult because of the ventilation requirements. But moving forward, I don't see any limitations for ammonia or CO2.
That is very promising to hear. Thank you very much. We'll take a couple more questions in the end if there are. So I think then we'll move on to our next speaker. We've got, oh, I know I'm going to say this one wrong. Xavier Deleg, sales manager from, how do you say it?
Xavier.
I got the Xavier part right. How do you say your surname? Is it how do you say your surname?
Sorry?
How do you pronounce your surname?
Deleg.
Ah, so I would have been fine. been around the French side, this side long enough. So you're from Sealy International. I mean, as a South African, we've actually done a lot of projects with the Sealy guys there, and we're privileged enough to see a lot of the applications and project sites. So it's quite interesting. You're going to be talking about low carbon cooling and indoor air quality. So over to you.
Thank you, Ilana. So good afternoon, everybody. Let me share my screen.
Perfect.
Starting from the end. Coming back soon.
Be a very interesting presentation
This
if we started.
Better, isn't it?
Yes, there you go.
Excellent. So good afternoon, everybody. Thank you for attending this presentation. Today I'm going to talk about low carbon cooling installation in Belgium with water refrigerant only using a Sealy International adiabatic cooling solution. And not only no dirty harmful chemical refrigerant is used, but energy consumption is up to 10 times lower than it will be with traditional air conditioning. So let's quickly introduce FAC. The customer would choose to use Sealy International cooling solutions for most of their premises in Belgium and for all their buildings since they tested these hyper-efficient technologies. For those who don't know FAC, FAC is a retail chain of sanitary, kitchen, and heating furniture in all Belgium. They have a large range of different building architectures with different activities. In total, FAC is more than 900 employees, 46 selling points, 15 showrooms, 3 logistic platforms, each one being more than 10,000 square meters, and 1 headquarters with offices. So several years ago, it became obvious to FAC that with climate changes, with warmer and warmer summer season, something should be done to ensure the well-being of people, but not at the cost of the earth. So their questions were about comfort, obviously, but also health, sustainability, productivity, and also cost and reliability. On one side, customers should be greeted in a pleasant atmosphere to increase their satisfaction, make them stay longer with a purchase intention. And on the employee side, the goal is to keep them focused, happy, and keep their maximum productivity. The problem with traditional air conditioning was not only the investment, but the running cost and the carbon footprint. Plus, on top of that, in most cases, using dirty refrigerant gas. This is how FAC came across Bioclima, the distributor of Sealy International, and they came across the adiabatic cooling solutions. So who is Sealy International? Sealy is the world's largest adiabatic air conditioning manufacturer with very innovative and hyper-efficient performances based on water evaporation only. The goal, the mission of Sealy International is to offer solutions to building owners and to building users to solve their running costs with when talking about indoor air quality and about comfort. Very often, one of the main arguments against cooling is a running cost. So Sealy solutions offer a drastic reduction of running costs with an electricity bill divided by up to 10 versus traditional air conditioning and even heat pumps. Sealy coolers also helps to reduce by 70 to 80% the carbon emissions. So this is a great help to manage a sustainable building and a sustainable business. Sealy International also offers to the building owners the most reliable and robust coolers with the highest performances. We have coolers running not only in Europe, not only in Australia, US, but in the harshest region in the world. And last but not least, and even one of the most important points in a period like the one we have been experiencing for the last 2 years with COVID, it's improving inside air quality. In accordance with all organization recommendations, Sealy coolers continuously bring fresh air inside preserving the essential moisture, not drying the air, and avoiding recycling stale air. So, when it comes to adiabatic cooling, there are two main technologies: direct evaporative cooling and indirect evaporative cooling. Breezer is our brand for direct evaporative coolers, which today is the largest technology used for HVAC premises. Very briefly, an explanation of the direct evaporative cooling. It uses the very latest and most advanced generation of pads called mini cell chill cell with a very specific design. These pads are soaked with water, and when the water goes through the pads, the water evaporates and the air temperature drops. The pads are on the far side of the cabinets. A fan pulls the ambient air from outside, and then once it has gone through the pads and the temperature has dropped, it pushed it inside the building. You can see here the solution process in an industrial building, continuously blowing a fresh, filtered, and healthy air. Climate Wizard is our brand for our indirect evaporative coolers. This indirect evaporative cooling is based on a counterflow core. It's a completely new wave of indirect adiabatic cooling. It's not a cross-flow heat exchanger, but a counterflow with an efficiency up to 136% of the wet bulb depression. Completely different to what was offered to the market so far, where the performances of cross-flow heat exchanger were around 65%. Here, we are talking of an average of 110, 120% efficiency on the wet bulb depression, and up to 136 in certain conditions. This technology has been installed at few HVAC buildings, mainly for their office applications, because Climate Wizard allows to decrease even more the temperature than direct evaporative cooling on the way down to the dew point. And very important, without increasing the moisture in the air. I'm going to show you a small video which will explain a bit more the process.
Climate Wizard is a standalone technology that delivers 100% cooled ventilation air. It uses significantly less electricity than a standard rooftop air conditioner and adds no humidity to the building. It does this by using an indirect evaporative cooling process. Let's explain that further. The heat exchanger in the Climate Wizard is made up of a series of alternating wet channels and dry channels, which are designed to transfer heat between them. Hot outdoor air enters the dry channels of the heat exchanger through a high efficiency fan. After air passes through the dry channels, a portion of the air is supplied to the building and the rest returns through the wet channels. This is where the evaporative cooling process takes place. The evaporative process cools the wet channel walls. As these walls cool, they absorb heat from the dry channel air, cooling the air delivered to the building. The portion of air supplied to the building is controlled by a damper that is set for the specific application. This process allows the Climate Wizard to deliver air to the building at a much lower temperature than traditional evaporative systems. This has benefits for both energy consumption and occupant comfort. Delivering 100% outdoor air, the Climate Wizard can improve indoor air quality by increasing ventilation rates to a building. Because it uses indirect evaporative cooling, where the wet channel air cools the dry channel air without any direct contact between the two, Climate Wizard does not add humidity to the building. So, although the system uses water to achieve evaporative cooling, only heat is exchanged and no moisture is added to the building. Climate Wizard is effective in a range of climates and applications, but the energy savings achieved increases as outdoor temperature increases and humidity decreases. So, Climate Wizard is particularly well suited for hot, dry climates.
So, the benefits of using Breezer and Climate Wizard at FAC are multiple.
Sorry, Xavier, can you
We
turn
have
your
already
camera
mentioned
back?
some of them.
Sorry.
The main one is the hyper-efficient performances that allow to considerably reduce the energy bill versus air conditioning, and especially during a heat wave and peak demand. Therefore, the building and business carbon footprint is also reduced, giving a very sustainable solution, as this is also not using, as I previously said, harmful dirty refrigerant gas.
Sorry, Xavier, can you turn your camera back on?
Sorry?
Your camera. You've turned it off. Sorry to interrupt you. Yes. There you go. Yes, you're back.
Okay, sorry for that. So yes, the Breezer solution is particularly suitable for large and very large buildings, like in the industrial and commercial sector. Using traditional air conditioning or heat pumps would have been very expensive in comparison for the FAC kind of buildings. And Climate Wizard would be more adapted when lower temperatures are required for comfort and also for process can be. And also what was very important to FAC was that the warmer the ambient air, the more efficient is the installation, meaning that even during heat wave, and we have more and more heat wave, even if this summer was not as the previous ones, city coolers provide always a very comfortable and healthy air inside. Here you can see some of the installation we have made for FAC. On all sides, you can see the coolers are installed on the roof. Depending on the architecture of the building and the requirements inside, we have used different kind of air diffusion. You can see the showrooms are a very nice design, and we have always integrated cooling solution with excellent comfort results. On this slide, you can see some retail center where we have large and high buildings. You can also see we are cooling some offices. Here, this is a small area, but we have also cooled some much bigger open spaces. In summary, since 2014, FAC has installed CD solution on 37 service centers, 12 showrooms, 3 warehouses, and 2 buildings with offices, for a total of 233 Breezer units, and more recently sold 3 Climate Wizard rooftops. This represents a total cooling capacity of more than 4,500 kilowatts. The Breezer and Climate solutions are used from March to November. Fresh, natural, healthy air is monitored with silly controllers according to the required temperature, to the required humidity, and more recently, according to the required CO2 level. At HVAC, the temperature is set at 24 degrees. And with the inverter variable speed fan, the energy consumption is optimized, maximizing the advantage of a superior temperature drop by sealing. So we estimate that this allows to save approximately 80% on CO2 emissions for cooling. The low electricity requirement also means that the installation does not require big power infrastructure, which sometimes can be a problem on some sites. So having low electricity requirement means also a lower investment in infrastructure. So for you to get a bigger picture of climate without possibilities, here are some typical applications. It is interesting to consider that the only limitation is our imagination when talking about the use of climate without technology. Obviously, this can be used in standalone cooling, where the building or the area is only cooled by climate without. But we can also have supplementary cooling. So with an air handling unit already installed, in addition, either because the customer has made an extension or the air handling unit is not providing all the capacity it should. This is possible with climate without because we don't add moisture, which was not possible with the direct evaporative cooling. An important one, also very important one, is pre-cooling, meaning cooling the fresh air of an air handling unit, increasing the capacity, the total capacity, and increasing the COP, decreasing the energy consumption. So that's interesting for a new site, as you will be able to invest in a lower capacity unit, or it's interesting on existing sites to improve the COP and decrease the energy bill. We can also have some high capacity installations made with modules, climate without modules. And we have also some customized installation for applications like data centers or in combination with heating. In conclusion, we are all very proud of these installations. The project has been monitored by Bioclima, the city distributors for Belgium. They are able to assist for every project with city support when necessary. They have all skills and documentation ready to work with customers, with contractors, and with specifiers. Bioclima is for Belgium. We also have distributors in most European countries. Not in most, in all European countries, most African countries and Middle East countries as well. And about Bioclima, as you can see, they have already made hundreds of installations in Belgium. So don't hesitate to contact them for any project. Thank you.
Thanks so much, Xavier. You can stop sharing there. Actually, interesting. The pre-cooling application you were mentioning, I actually saw a couple of those installations in South Africa where specifically there was like aging chiller plants and there was specifically a hospital application and they couldn't afford to replace all the equipment. So they just actually, it was cheaper to pre-cool the air and then actually extend the life of the existing equipment than to throw out the whole system and start over with a new system.
Correct.
And then the same on the electricity saving, for instance, especially on I think it was wineries or some farms, for them to have put in any other system, they would have had to get an entirely new electricity connection that could handle it. But because of these units, they could have just, actually saved them some money. So I think
cooling is very interesting. Also, as soon as you need fresh air.
So specifically, because this was a hospital application for the theaters, yes. This was great. Can you stop sharing?
Yes.
And it's always the hard part, and then I'll hand over to the last speaker. I see we already got some questions coming through. I'll take them after this presentation. But for now, we've got one more session left. Well, I mean, one more set of speakers. I'm going to hand over to Martin Lazar. He's the co-owner and board member of AKS Lazar. And they're going to be talking about HDI inverter air water heat pump models with R290 refrigerant, which is great because we've been talking a lot about all like ammonia and air and CO2. So let's see what R290 can bring. Thank you so much. Over to you guys, Paul.
Okay. Hello, everybody. My name is Marcin Lazar. We'll show you a presentation about inverter heat pumps working on natural refrigerant R290 by HKS Lazar. The presentation will be about methods of increasing COP, which we use in our new HTI 20 model. First, I would like to shortly introduce our company. We are a Polish company based in the south part of Poland. HKS Lazar is one of the biggest producer of pellet boilers in Poland. In heat pumps, we are involved about 4 years. 2 years ago, we started production of our first heat pump, model HT10. This is on-off model with very interesting casing and extraordinary casing. And now we are launching new inverter model HTI 20, which received some very interesting solutions regarding electric power supply, cooling mode, and power modulation, what we call keep power system. We are selling our products under our own brand, HKS Lazar, all over Europe, and we've got some also experience in OEM production. And now my colleague Paweł will tell you about main technical stuff.
Okay, hello, my name is Paweł Matusiak. As a technical consultant, I will say something about technical issues. So let me tell about our experiences with inverter, air-to-water heat pumps, with propane as refrigerant. And on this presentation, I will talk about problems which we have met and solutions which we have found. So let's go on. Our project was focused on several topics, challenges to overcome or to achieve, such as high COP, high heating capacity, use 4 models of compressors, scroll and rotary, use popular current components, and use new type of wing shape evaporator. And after 1,000 working hours and fulfill operation winter and summer, we hadn't noticed any compressor damages, but it was not the end. New improvements usually demands new construction, new design. So let's talk about it. So first challenge, let's start from refrigerant line improvement. We noticed that, I suppose everybody know that propane behaves different than, for example, F-gases. Propane expands very, very quick inside the evaporator tubes and breaks heat transfer. So generally, even flow of refrigerant was needed. So our solution is special 3D internal modifications of groove tubes. Change copper tube into ring chamber. Refrigerant flows very close to the tube edge with different speed and expands slower. We can control it. This solution gives us better performance because the active surface works more effectively. So next challenge, we noticed that because of PAD regulations, we can't use bigger evaporators, and propane has got many charge limits. You know that. The same, but solution, the same special 3D internal modification, which I mentioned before, it gives us 50% reduction of evaporator inner volume. So this is the example. We got 9 kilowatts cooling capacity, but instead of 6 liters, we've got 3 liters inner volume in evaporator. But internal modification is not all. Now, we notice that especially in propane, we have to pay attention for every disturbance in airflow. So solution, usually fan position has got bad influence for airflow velocity. So different pressure drops make many problems. So cover design is not only solution. We notice that wing shape evaporator allows to install fan very close without any disturbance in airflow. And second, we divided wing shape evaporators for 2 sections, upper and bottom, and each section consists of 3 segments. So those segments have also different louvered fin space to make additional corrections. So different fin spacing solve all problems with, for example, icing, and evaporator shape solve problems with fan position and airflow. But it was only theory. Let's look at the performance. Everybody asks me about one thing about superheat, and that I always say that oscillation of expansion valve it's first problem, and high superheat is second problem on propane. So we can see on the left is very interesting RD entitled Experimental Evaluation of Air-to-Water Propane Heat Pumps from Sweden. On page 44, it said experimental showed that the stable control of superheat to be as low as 5 K at the evaporator outlet was hardly possible. On the left, we can see very high oscillation at superheat 5 K, but please look at the evaporator on the left with different temperatures. So now, could you please look at our RD on the right? We've got 5 K. And no oscillations, but please look at our evaporator on the right, almost the same temperature on all the surface. Now let's look at what happened with COP when the superheat was 5 to 4.5 K during 20-minute test. We've got A2W35 and COP was 4.83. And second parameter was A7W35, COP was 6.45. So probably you will ask me about the lowest superheat which we achieved. It was 1.2 K. Okay, so now let's have a look on 4 models, inverter models. You might be surprised. The larger unit is 16 kilowatts, but it's 16 kilowatts at A-10 W35. So it's the strongest in residential inverter air-to-water heat pump with propane as a refrigerant for now. We've got some delay according to the COVID, but key mark certification is in progress. Now let's talk about cooperation. All models are OM ready with Carol as a main driver and full internet access by mobile app. So if you had any questions, I'm concerned that this presentation will be published on ATMO website after this conference, and you just can get it and send us email. And thank you for watching. I'm sure that we'll meet soon. And special thanks for Karel, Kaori, Hydria, and all involved companies. Thank you.
Thank you so much to you both. And yeah, you are right. The presentations will all be available on the ATMO website by latest Friday, actually, from the team. You can stop sharing, then we can take a couple of questions. Well, I actually have a few here on the website. Let me see.
Wait a minute.
No problem.
Yes.
Okay. There you go. Now we're all back on screen, so everyone can turn on their cameras again for let's have a bit of a discussion. I think we're actually getting quite a few questions for you, Kenneth. So I hope you're ready. We have one here from Gregory saying it was interesting to see I think this one is for you, the DH network example. Was that your presentation? I think it was the timing. What about the electricity use? Can it be a deterrent in countries with poor electrical network or a high cost of electricity? Was it that one?
Of course, there is some countries where it's we see a bigger uptake than others, and one of the things is, of course, the cost of electricity and how green the electricity is. But I think there is a decarbonization of electricity grid across Europe going on. So it will spread out across Europe, and it's not in the same speed everywhere. But I think if we look towards 2050, I think it will be very much across all of Europe. You will see a big heat pump uptake into the district heating sector.
Great. We also have a question also for you, Kenneth, from Colin Bootsveld. He's on Gateshead. Why did you not distribute the 15 degrees Celsius temperature, perhaps via a heat exchanger to a closed circuit? Then do you not need a lot of insulation and each household can run an efficient small heat pump?
First of all, you can't the water from the ground source. You couldn't really take out to the household because it has a bit of impurities in it, so you don't want that into the household heat exchangers. But then secondly, it's also more costly to have thousands of smaller heat pumps than having one big one. Of course, if you could probably save someone the insulation of the pipework, but I don't think district heating pipework. But I don't think that's a big issue when you need to dig up the ground and everything to lay down the pipe. I think the insulation is a smaller cost of the whole installation.
Great. Thanks so much, Kenneth. We've got a question. We've got a question here for Powell while you guys are unmuted, from Eric asking, what protection method do you use for avoiding propane from entering the secondary circuit? This is for the
propane heat pumps are hermetic, so it's just fabric solution.
Okay, so that's not a problem at all. That's great. And then we've got another one here for Xavier from Menno asking, what is the air volume net of the Climate Wizard, and do you also need a third back as process air?
For Climate Wizard, we have units going from 3,000 cubic meter per hour to 26,000 cubic meter per hour, considering that we can, with the big ones, we can twin them. So that's for the, I would say, finished goods units. And then we can work on specific installation with modules. But most of the time we work with the existing units and we just add them together with the best distribution, air distribution.
Great. I think that's the ones we had online. I just wanted to also check while we added on the, because I also want to ask the other panelists the question I asked to Kenneth that's on the poll about how long you think Europe needs before it can switch to natural refrigerants. Currently, the poll is on 52% believe we need 6 to 10, but at least luckily no one says it's never possible. So, I mean, maybe let's start with you, Graham. What do you think how the journey is going to go for specifically on the industrial air conditioning application side in Europe only? Well,
I think for industrial refrigeration in the UK, we're already well advanced. Lots of our industrial customers use ammonia or natural refrigerants. And there's a big push now to transfer over to natural refrigerants. I don't think we'll be completely there in the next 6 to 10 years, but I think we'll be close.
And on the air conditioning side, as the journey, is that specifically for refrigeration, or does it apply up to both?
I think air conditioning is possibly a little bit harder to get. Certainly, ammonia and the hydrocarbons in there, just because of the difficulties of the hazardous refrigerants or flammable in office buildings and some of the places where it's going to need to go. But I think we'll get there eventually.
Hopefully it's a bit quicker on the industrial side. I do think our commercial air conditioning is probably where I see the most challenge, I think, on the competition from specifically on the VRF and those equipment. But I think industrial, we should have a good chance.
Industrial, yes. I think it's the commercial and the domestic air conditioning is a good challenge.
Yeah, I think, but hopefully on the industrial it can go a bit quicker. What do you think, Kim? How long it will take? I mean, not everyone is as advanced as Denmark, but for the rest to all catch up. Oh, I can't hear you. Your sound, it's unmuted, but there's no sound coming through. Not sure what changed. Maybe it's the earphones. Oh.
Here, can you hear me now?
Now we can hear you, yes.
That's better. I think there's a big difference between air conditioning and heat pumps. I do see much more time. We need much more time for air conditioning. Heat pumps in general are challenging to any refrigerant, but I think we have some good opportunities for bigger heat pumps with ammonia and CO2, and those two refrigerants would take that market, and we already see that. For chillers, I think it's different because for very large capacities for natural refrigerants, we do not have turbo machinery. So to substitute these very big HFC or HFO based turbo machinery in large air conditioning, that there we need some more time to invent new technologies there. So I think there's a huge difference between heat pumps and air conditioning.
Very important point there. So I mean, is that not something that large capacity, is that not something that can be served by ammonia that you're talking about? Is that on the chiller side, is that still a problem? Okay, that's good. I mean, that's nice. And Xavier, on your guys' side, how long do you think it will take? If you look specifically on the, I mean, because I think that's the one thing that's nice about the Sealy solution is that it is for the commercial market that actually can take market share. But do you think there, first of all, there's enough products available in the market for natural refrigerants to completely take over in commercial industrial air conditioning? Or do you think there's still some time to go and we need new products? Many questions in one.
Yeah, on our side, we are ready to produce as much as the market could do. It's more a question today of the technology on our side is ready. I mean, water is completely natural, it's clean, energy efficiency is at the highest level with direct or indirect, and with indirect we are able to work on all kinds of applications, from residential to industrial to process. Today, and I've heard this yesterday by one of the speakers who was telling training. So yes, training consultant, training specifiers, but also we need to change people's habits. And it can come very quickly because we see people's minds is changing, especially in Europe. But what we will need is a strong regulation. I mean, a few years ago, nobody would have thought that we would talk about electrical car being as big as it is today and as big as it's going to be tomorrow. So regulation really makes everything. And I think regulation could be a bit stronger as well.
And it's always policy driving it. You always need that carrot or the stick, you know, like the restrictions or the incentives for the market to actually move.
Correct.
That's true. I mean, Luca, on your side, what do you think specific if you look at heat pumps, what are the biggest challenge currently to switch over completely to natural refrigerants? If you look particularly on the air conditioning side, where do you think the technology is still not there yet, or where are the challenges in terms of convincing the end user? What is the struggle?
Yes, I think that nowadays the technology is ready to grow in all of the most important countries in the world. Even the necessary devices are available on the market from several suppliers. There are several manufacturers of CO2 compressor racks, both for refrigeration and HVAC field. So that I think I always say that the CO2 is growing from the lowest capacity up to the huge capacities. So from the domestic up to the industrial needs, and in the HVAC sector as well. Our installation is an example how CO2 technology is able to replace the old technologies, both for heating and cooling, and we think that CO2 is the obvious choice in our application field.
I think it's the exciting part. Thank you so much. The exciting part is to see that there is actually every year just new technologies coming and new products and new solutions. And I think we're going to, even just if you look how far we've come since we had that conference, the air conditioning conference with DTI on natural refrigerant products, I really think that even in Europe, where people don't necessarily always think that they need lots of heating and lots of cooling, sorry, the heating we definitely need. There's definitely now a lot of more investment in the R&D side and the air conditioning too. So I think this is something that's going to rapidly change, but as you said, it also we would need the demand and from the customer side, and we would need the policy to also catch up with that. So hopefully the new round of F-gas regulations also looks at the air conditioning side. But yeah, I just wanted to thank all our panelists today. I don't want to keep you all here. It's been a long session. Thank you so much and keep up the good work. And yeah, we have one more closing session today, and I think the last session is also still going, the parallel one. But thank you everyone very much for your time, and take care. We'll be hearing from what you're doing. Thank you.